Do you want to start learning animation? Or maybe you just want to boost your already existing animation skills? In that case, hello and welcome to this tutorial series, which is going along the 51 animation exercises. In case you don't know what that is, we have a list of 51 great animation exercises on animatorisland.com. If you made your way through all of them, you are probably a pretty decent animator at the end. In this tutorial series, we're actually going to do them step by step. And while we're doing them, I'm gonna teach you everything that I know about the principles and the reasons of why we're doing the things in this way. You might be thinking for the very first exercises that they're kind of basic, but I tell you, these exercises are the best to really get your animation foundation right. Even Disney trainees, when they come to Disney, they have to prove once again that they can do the bouncing ball, that they have mastered animation through this very simple exercise. At the beginning, we're doing everything in 2D and 3D. And for the first few 2D exercises, you don't even need to be able to draw. And you don't need to invest into any expensive animation software because we are going to be using completely free and open source animation software, Krita and Blender. So I hope you are along for the ride. First up, let's have a look at how the illusion of motion actually works. A lot of the times, the illusion of motion is explained by a term called persistence of vision, but by now, scientists are pretty sure that that is not what creates the illusion of motion. The persistence of vision says that images shown in quick successions, images in quick succession will blend together to one image. And this helps us, for example, to not see pitch black every time when we blink, because the image that we were seeing previously is still retained in our eye. And here's another nice demonstration of persistence of vision. Maybe you have seen one of these before. If we spin the disc really fast, the two sides of the disc should blend together to one image. Now, I'm not sure how well the camera will capture this, but let's try it. So if it's not persistence of vision, what else is there to explain perceived motion? There are two more phenomenons. One is called the phi phenomenon, and the other one is the beta movement. And the beta movement is the one that we are actually looking for. In the beta movement, we have similar images that are just, slightly different, enough to create context between the images. And if these are playing in succession, even at a low frame rate, we already construct a context between those images. For example, you can see that it already feels a little bit like there's a teapot traveling from left to right, changing colors, which is a pretty weird thing if you think about it, because in our everyday life, we don't see teapots moving on their own or changing colors. So scientists by now are pretty sure that this is a cognitive process, not a chemical process that happens in our eye. The most simple animation that we can do only has two drawings that we can flip back and forth from. And it already contains an information that isn't in any of the two drawings alone. Let me show you what I mean. Don't worry about following along here. I'm going to explain the software to you later on. Just focus on the theory for now. I have a timeline with 2 frames, and I already have one ball here, and I want it to travel horizontally to the right. Now, on frame 8, I put another ball in a little bit of a distance down. I can activate something called onion skin, so I see the previous drawing shining through, so I can make sure that, I'm not putting it here. I only want it to move horizontally, so yeah, so I put it here. And if we play this back and forth, we have a little bit the impression that there is a ball moving left to right. Now, the difference of these 2 frames on the timeline, one being here on frame 0 and the other one being here on frame 8, this distance is called timing. But there is another very important kind of distance in this little example animation, and that is the distance between the two drawings. This distance, it's called spacing. These are important animation terms, and whenever I say an important animation term, I try to mark them with a star. In this case, they're also part of the 12 principles of animation. But let me explain you spacing a little more. We have an animation with the timing of 8 frames, but we can change the spacing to create the illusion of a different speed. Let's keep drawing in the same drawings, but this time I'm going to put the first frame, I'm going to put the ball exactly where it is up here too, but in the second frame I'm going to put it over here. So what we have now is 2 balls moving with different speeds, because in the same amount of time, this ball here is traveling this distance, while this ball is traveling this much larger distance in the same amount of time. That means this ball is slow and this ball is fast. But that's not all the fun things that we can do with spacing. We can actually use it to put yet another information in there. When we add drawings, what we could do is let's go exactly in the middle between the 2 frames time-wise, and let's also draw a ball directly in the middle between those 2 keyframes. But this is not giving us a new information. We still have 2 balls moving with the same different speeds. But what we can do to add a new information, instead of adding once again a drawing exactly in the middle, we're gonna add one that is much closer to the original position. Let's say much closer. The spacing between the first and the second frames, first frame to the second frame, is relatively small, while the distance between the second and the third frame is larger than the distance was before. This means we increased the spacing, and this gives us the impression of acceleration. And we can also go in at the end of our little animation, and here at frame 6, we're going to put in a new frame. And once again, we're not putting it in the middle because that would just keep the speed that the ball was already having. But we're saying, okay, you are slowing down now before or while you move towards the last frame. You're doing that in a way that looks like it's slowing down, and this is the result. One thing that especially 2D animators use to plan their animation or to visualize what spacing they wanted to have are timing charts. But I've also seen a 3D animator plan the motions of different body parts with that. Now, a timing chart is looking like this. You mark the first frame and the last frame. You connect them in a way like this. You could use this to indicate how the motion is actually supposed to go, but in our case, it's just a straight line. And then usually you do that before you animate, and this time we do it afterwards. And then you mark where you want the drawings to go, and you can use that to communicate with another animator. Or if you have a complex animation, with all the different body parts doing different speeds at different times, you can use it to note down the different spacings that you want everything to have. And here you can now clearly see that these spacings are getting larger, and then from larger it is getting smaller again. By now we are slowly running into a little bit of a challenge, namely that different people use different terms to explain the same things. For example, colloquially, you would say speed, a physics professor would say velocity, and animators usually talk in terms of spacing. And I try to always give you as many terms as possible so that you always know what people mean when they talk about this. But the animation terms are probably the ones that you should definitely keep in mind. And now for this, the term used a lot is ease in and ease out. If we define these here as the keyframes, then looking from the view of the keyframe, we ease out of this keyframe and we ease into this keyframe. Of course, this example was not very fluent looking because we're using so little frames. If you can use the same patterns that we just learned about with more frames. And here's an example how this looks then. I think this is over the stretch of 20 something frames, 22 frames. But one of them at the top has ease in and ease out applied, and in the one at the bottom, the spacing between every frames is the same. They start and stop at the same time. So in animation terms, what they have the same timing. A motion like the one down here is called a linear motion. So linear is when all of the frames have the same spacing, and motions that are completely linear from beginning to end are very rare in nature, because most of the time you need to build up speed, or you need to catch something by slowing it down. Now, a motion would not slow down if, for example, something is falling or something is going like at full speed into a wall. Then you don't have a deceleration, but you still, this energy had to come from somewhere. So most of the time you have either a build up or a wind down. And most of the time, pure linear motion looks wrong and mechanic. Maybe there are robots who can build up a linear motion immediately and come to a stop immediately if they're built that way and light enough. But in most cases, you need to think about where's the energy coming from? How is it building up, or how is it being caught? And then you don't have a linear motion anymore. You already know the terms for the ones above. We have spacing that gets larger and larger. So we have an ease out. And then we have a point where the spacing gets smaller and smaller. So we have an ease in. Now, the important thing is if you dedicate to ease in or ease out, that you need to keep this pattern going. If you break it, you will have a weird jerk motion in your animation. So for example, if you set that in this part of the animation, you want to do an ease out, you can't have a frame where you have the spacing here and a frame here, because then it will look like it got faster and then it somehow got stuck and got slower again, and then it immediately gets faster again. You usually don't want that. If you don't have a reason to break this pattern, you should not do that. But now enough with balls moving from left to right. Let's do something more fun and something more practical. Let's look at how to animate a mic drop, and let's talk about a giant's butt. Welcome to Mic Drop Physics 101. And now we're getting close to what this tutorial is actually about. You're going to learn how to do the bouncing ball. And the truth is, if you already started or, in the near future, making the bouncing ball will just be a couple of clicks for you. It's really easy to do. But the thing is, this exercise is actually not about the buttons and the keyboard shortcuts that you need to make them. It is actually not even about making a ball bounce. Like, you don't want to make a short film out of this. No, that's not the point here. The point here is to understand the physics behind it. And more importantly, this is all about the free fall. And the free fall is in everything, and it will be in your more complex animation in the future all the time. When a character lets them say fall into a couch, or if you just let your arms drop, this is the free fall at work. So you really need to know this, because you need to put it in almost all of your animations. And the reason why the bouncing ball is so great for doing that is because it's an opportunity for experiments. Because it's so easy to do, you can do it again with different parameters, try different ways of animating, try different timings, different spacings, and just see what happens, how it feels different. And we, at the beginning, will focus a lot on the real physical laws behind it. And you might be wondering, why do I, as an animator, need to know that? I only want to do cartoon physics. Why do I need to know real physics? And the reason is because if you have realistic physics in your animation, you can create a more tangible world. You can make a world where falling actually hurts, where falling feels dangerous, or where heavy objects actually, feel heavy and threatening. If you need this in your animation, then you need to apply the laws of physics. And even when you want to do cartoon physics, it's exaggerating the real world. And in order to exaggerate something, you need to know first what it is that you are exaggerating. Makes sense, right? So let's drop something. And I was thinking, I never say something clever in front of a microphone, so I should use this opportunity to do a mic drop. My mic drop height is 1.20 meters or 3 feet 9. And if I'll let the microphone go, I can see in the video footage, it's exactly 1 millisecond long, or half a second, as some people would say. Now let's think for a second about what happened here. While I was holding the mic, there were two forces applied to the mic. One is gravity pulling the mic down, and the other one is my hand. And when the mic is completely still, the force of gravity and the force of my hand is exactly the same. That's why nothing is happening to the microphone. Now, if I open my hand, the force of my hand is immediately gone, and only the force of gravity is affecting the mic. And this actually causes the acceleration of gravity, which is minus 9.81 meter per second, to accelerate the mic towards the ground. And because scientists were getting tired of just dropping objects to see how long they fall, they came up with clever formulas like this one, where we can just put the height that we already know and the acceleration of gravity that we already know, and then we get this, an equation that we can actually solve towards the time, and with some math magic we get the result that our microphone falls for 0.49 seconds. And when I first calculated this, I realized how I always somehow assumed that it would be shorter. I mean, a half a second is relatively long. It's time enough to say 1 millisecond. And that is kind of long. So what about a higher distance? Like, let's take a 20 meter tall building, which is about 4 stories or 65 feet. And again, we put that in the same formula, do some math magic, and the result is 2.02 seconds. I think this is really long. This is 1 Mississippi, 2 Mississippi, and that is something that you need to know when you animate like giant spaceship or giants. For example, if you have a giant whose bottom is up 20 meters in the air, if they want to sit down by just like letting themselves fall, they will take 2 seconds to reach the ground. And if the giant is not just letting himself carelessly fall, but like really getting slowly comfy, then this motion would be even longer. I don't want you to learn this formula by heart or something like this, but I just want you to keep a general idea in mind. And the big takeaway here is that big objects moving far away, they appear slow. On our website, we have a free fall calculator, and I may change the look of it a little bit, but the basic function should remain the same. You can just put in a distance, and then you can calculate the fall duration. And you could use this to play around a little bit. But let's be honest, most animators don't want to be bothered by doing math. So let's have a look at how you can cheat and simplify this process. I want to show you some easy ways to animate the free fall, and we're gonna start with the traditional handmade way. We're actually gonna draw every single frame in a 2D software. And 3D animators, I would ask you to stay with me, maybe even try this yourself. You don't need to actually draw the frame. If you can't draw, there are some tricks how you can help yourself so that you don't have to actually, you don't actually need a tablet or anything to do this exercise. Now, the first pattern, the first rule that I want to show you is the odd rule. And if you want, you can already do this alongside with me. I'm using an open source 2D drawing and painting software called Krita, and you can download it for free on krita.org. So this is more or less how Krita looks when you open it for the first time. You can make a new file either by going here at File New, or you just press in the middle of this gray area. A good size for any animation project really is 1920 pixels wide and 1080 pixels high, because this is the full HD video standard, the video standard that most televisions across the world use at the moment, and also many cinema resolutions are around this full HD resolution. Now this will change one day we'll get 4K, but for now keep 1920 times 1080 in mind, and 72 pixel per inch is the pixel density on a digital screen. So this is okay. For printing, this would be too little, but we're just doing a digital project here. So I think this is all the settings we have to do, and we created our first project. Now the interface is suited more for painting at the moment. So we have to change our workspace from the default workspace to the animation workspace. And then one thing I also like to have at the right side is the brush presets, so we can change quickly between different brushes. And you find the brush presets here in Settings, Dockers, and here they are, a bunch of drawing tools that we can use. Another way to get some drawing tools or to build yourself a quick access bar is when you click the right mouse button. Then you can change your color here, and you can put in some brush presets. There are some predefined views already. You can have paint tools. In our case, I think we would want to have something like sketch tools. And yeah, let's go. The most important thing, of course, for animation, and this is what the animation workspace actually introduced, is the timeline down here, which is where our animated frames will find its place. Now, before we start animating, you need to make a frame on the timeline, because if we already put something on this layer and then create a new frame by selecting the first frame and clicking here, you will see that our frame has been cleared. It's an empty frame right from the start, and the drawing that we already did is gone. So make sure that before you start animating, you already created your first frame. I think alternatively, you can also right-click and make a new frame from here. If you have a drawing tablet or a Cintiq or something like this, you could now directly start drawing. But, you know, if you're not that much into drawing, I don't blame you. You can use, for example, the ellipse tool right here. And it's actually going to use our brush. So we can just do this and get some very nice sketchy lines. And of course, you can hold down Shift to get perfect circles. So yeah, if you want, you can just keep doing that. But before we start animating, for the odd rule, we need something like a grid, and we can make that really roughly. We just need we just need to draw some spacings here. 1, 2, 3, 4, 5, 6, 7. Okay, I got 45 units from top to bottom. That should be enough. And the reason why we need this grid is because we're actually going to measure our spacing between the frames, because the odd rule says that the spacing increases to the next uneven number. This is actually physically accurate. So if we're gonna animate according to the odd rule, we will actually get a realistic fall. And from the previous chapter, we know that, you know, when we did the mic drop, dropping something from 1.20 meters takes approximately half a second to fall, which in a 24 frames per second document, as mine currently is, you can see that down here, this would be at the 12 frame mark. Personally, I don't like animation software that starts counting the first frame with frame 0, because, you know, this frame actually exists. This frame is frame 1. Adobe After Effects, for example, does that too. I don't like it if the first frame is frame 0. So what I'm going to do is say my start frame is actually frame 1. And also, I think I'm going to take this grid off this frame. I'm just going to empty it and put it into a new layer. And this way we can always see the grid even as we start making new frames here. What we are going to do, we are not actually putting a drawing on every single frame, because there's a lot of work. And many animators found out that in many cases, 12 frames per second is already enough. Only when you do very fast motions, like running or some physical fighting stuff, there's some stuff that you can only do on higher frame rates. But a lot of the times, if you see like animated television, they work on 12 frames per second. But to keep our option open, you know, we might do something really fast in the same film. We keep our project settings at 24 frames per second. And what we're going to do is we just draw on every other frames. And this is what animators call working on twos. And you drawing on every other frames means that you are working on twos. Now I'm going to use the ellipse tool too, and I hold Shift. Well, I have to click first and then I hold Shift pressed to get a nice and round circle. Now we can use this transform layer tool here to transform our, this is the pivot point, to transform our ball. I'm going to put it right here so that the bottom of our ball is lining up with a unit in our grid. So this is the first frame. The first frame is being held for 2 frames, for frame 1 and frame 2. So the next frame we create here on frame 3. Right click, new frame, if you would be drawing this by hand. To see the previous drawing, you can switch on the onion skin for the particular layer by clicking on this little lamp icon here. And now you can see that our previous frame is showing through in red. And there are some options that you can use. If you click on this onion skin symbol, this window will open and you can put in how much you want the next and the previous frames to show through. Now, because I'm working, I want to keep working with this perfect circle. I'm not actually, you know, if I would be drawing frame by frame, I could now draw the next frame. But I'm gonna make my life even easier and cheat even more. I don't make a new frame from scratch. I copy this frame by holding Control and dragging this frame onto frame 3. Now you can see we have a new frame indicated by the blue box. And we can just take this ball and now move it down onto the height of the first unit in our grid. So the first spacing according to the odd rule is 1. If we go on our grid layer, we can actually write this down. We already did the first unit down. And according to the odd rule, the next uneven number is our next spacing, 1, 2, 3. So the next ball will be on that height over there. Important, we need to switch the layer again. Now click on that previous frame, and with control click and drag, we can pull it out 2 frames. Of course, we need to modify it again with the transform tool over here and put it on the next spacing. Maybe we could switch on onion skinning to see how it lines up. Yeah, this looks quite good. The next uneven spacing, the next uneven number is 5. 1, 2, 3, 4, 5. Over here. Again, control click, control and drag. And we just continue like this until we have reached frame 12. You might be wondering why we're actually ending up on frame 13 is because, you know, we already count starting with frame 1. So if we have a duration of 12, then the next step, the next big step in our loop, in our animation, is on the frame 13. This actually took a while for me to wrap my head around. If animators are talking of stuff happening in 12 frames or in 6 frames, like walk cycles or something like this, or dance patterns, what they mean is a length of 12 frames. So the end or the next animation, the next pose is 1 frame further. Another thing that you might be wondering about is while I was drawing onto the layer with the grid, it created new frames. You see that? It created new frames of the chart expanding. And this is because of this option on. It's called auto frame mode. And basically what it does, if when I start drawing something, anything on a layer that has animation on it, it creates a copy of everything that is already on this frame, plus whatever I started drawing. You see here it was empty, and then when I put in the squiggle appears at frame 21. This is not necessarily what I want, because I just want this grid to be here stationary, so I'm going to delete all of these frames and just move the last frame here. So right from the beginning, we have our grid. Now, this is actually a physically accurate animation. We have a ball being dropped from the distance of 1.20 meters, and because of the odd rule, it's animated physically correctly. The cool thing is that this odd rule even applies to rolling or falling on slanted surfaces. For example, if you would roll the ball down a surface like that, you know, the distances 1, 3, 5, and so on would still be the same. So this is not only applying to free fall, this is also applying to any, you know, sideways sliding and stuff like that. Another very rough rule that might help you to estimate if an object is falling correctly is that if it is a fourth of the way down in half the time, then you got an accurate animation. You can see that right here, right in the middle. If we cut this in 4 equal, more or less 4 equal parts, then we have a fourth of the distance at frame 7, which is directly in the middle of our animation. But you know what? Animators want to have it even easier, counting to the next uneven numbers. Who needs that? We need a more visual system. And this is a system that has been used by 2D animators for a very long time. It's always using the half distance to create eases. All you need for this is to know your first frame position and your last frame position. And then you can always go exactly in the middle, always halving the spacing to create, in this case, an ease out. Here and here and here and here. And now we can animate that onto our ball layer. This time I'm gonna actually draw. We can use the arrow keys to go back and forth on the timeline. All right, I'm gonna put in our next frame. Next frame. Next one. And because I'm working on the layer that we already have, I'm not copying what I saw previously, but you know, it's drawing it on the same layer that the other animation is in. And here is the ground. Now, if we play those two back to back, maybe let's change the length of our animation, which we can do here, to frame 17, so we can see it looping quicker. Yeah, as you can see just by looking at the distance, the cheating way, the halving way, makes the animation slower in the beginning here and snappier in the end. This is actually playing into the hands of exaggeration, making stuff more snappy and more powerful. So yeah, this is the method that a lot of animators use. It's not 100% accurate, but you know, it gives you an ease in and it gives you a very large distance at the end. By the way, if you would record a ball falling, it could be that you get in a frame right before the impact that you see a ball being here. This can happen when you're filming, you know, if the camera happened to make the photo in that moment, then you have the ball close to the ground. There are some animators who say that this is okay. I don't like it because, yeah, of what I talked about earlier. You know, if I want to have an ease in, I want to have a ball accelerating because of gravity. I don't want it to cushion right before it hits the ground. I want the impact to be really there. Now, there are some animators who actually make an additional frame here. So there's a slowing down before the ball hits the ground. So it almost kind of looks like the ball is like stopping and really slamming into the ground after a short little break, if you will. I'm also not a big fan of this method, but you know, just so you know, there are different ways to do this. I personally like to have it as pure as possible. You know, if I decided to make an ease in because gravity is working on this ball, then, you know, I should do it how it is in its purest form, that the spacing is always getting bigger. We can turn this thing easily into a loop just by copy and pasting frames that we already have. We don't even need to draw new frames. And the reason for that is on the way down, all that happens to the ball up here when we let it go is that the acceleration of gravity is speeding it up faster and faster and faster, as you already saw. But here, when it has the most amount of energy, our hypothetic material is deflecting that energy and putting it right back into the ball. But now the gravitational acceleration is actually fighting against the ball, reducing this momentum until it reaches the part where it no longer has any momentum or velocity in the upwards direction, and then it's coming down again. So all that we have to do is just maybe remove this artifact here. All we have to do is just always go one frame back, hit Control, and drag it over to be our next frame. Go to one of the previous frames, dragging it over one frame more, dragging it over one frame more, dragging it over, and now we can set this at a loop. Our loop is actually going to frame 24 because the frame 25 is identical with frame 1. We don't need to show that 2 times. If we would, then this frame would be shown 3 times. And if we hit play, we can see the ball falling down and jumping up, down and up. And yeah, congratulations if you followed along. If you did this for the first time, you created your first bouncing ball. One very physically accurate and one lazy one. In the next segment, we're going to have a look at how to do a bouncing ball in 3D. And this time I'm going to ask the 2D animators to stick along, because there's actually a lot of 2D animation software where you can animate in a similar way. What this way is, we're going to talk about in a little bit. First, I want to introduce you to this software. It's called Blender. It's basically a complete 3D pipeline. You could make a full feature film in Blender. You can download the software under blender.org. And if you open it for the first time, it should look a little bit like this. You need to navigate in 3D space with the middle mouse button. If you just click and hold and drag the middle mouse button, this is what you see. If you hit Shift and the middle mouse button, you can drag the view like this. And if you hit Control and the middle mouse button, you can zoom in and out like this. And I think also with the mouse wheel, yes, you can do this. You select an object by right-clicking it. In this case, we have a cube, a lamp, and a camera. With A, you can deselect everything or select everything. If you hit the comma key on the numpad, you are focusing on the selected object. And this is very helpful to, work on different things at different times and make your view orbit around what you currently want to focus on. There also is the command Shift-C, which does 2 things. Shift-C centers your view, and it also resets this 3D cursor. The 3D cursor is where you create, this is the position where you create new objects at. And sometimes you can also use the 3D cursor to rotate objects around it. So if you hit Shift-C, your view is centered and your cursor is in the middle again. Now let's delete this cube because we don't want to do a bouncing cube. We want to do a bouncing ball. So all we do is we make sure that we have this cube selected, and then we hit the delete key. It's gonna ask us if we really want to do it, and you can just click on delete and then it's gone. And in its place, we're gonna make a new object by clicking on add mesh and UV sphere. And here we have a new sphere. Now we can hit the tab key to switch to something called an edit mode. And the edit mode is actually used by modelers when you want to make a form that is a little more complex. You can make a form out of all these little points in 3D space. As you can see, I'm going in and out of edit mode, and you can do that with the Tab key. In Blender, like in many other animation software, objects have a pivot point that they rotate and scale around. You can make your life a lot easier by choosing the pivot point smartly. For example, I know that later on I want to squash the ball, and I can squash the ball by using S and the middle mouse button and dragging the mouse down. What we can see is that it's squashing towards the center of the ball. But if the ball was on the ground, in order to keep it on the ground, I would have to always translate the ball down so that it is on the ground. For example, if I later realize that the ball is squashing too much, then I have to de-squash it and push it back up again. Or if I wanted to squash more, I have to squash it more and put it more towards the ground. This kind of counter animation you should always avoid if possible. And in this case, we can easily get around this by having the pivot point at the bottom of the ball. To get the pivot point there, we shift all the vertices, all the 3D information of the ball up so that the pivot point is at the bottom of the ball. We can select all of our 3D points in edit mode and click on the axis, on this axis arrow, to move it up. If we hold Control, it will move along in fixed increments, and there actually is an increment where the pivot point here is exactly at the bottom. Now we can squash the ball and it stays on its place down here at the bottom. We already used this manipulator where you can just click on any of the axes to move our ball around. You can switch that on and off here. I think this type of manipulator is very useful. I usually also activate this manipulator, and you can see them both at once. If you hit the Shift key while clicking on them, you can have the translation manipulator and the rotation manipulator at the same time. Rotation doesn't make much sense anymore with our pivot point being down there. But if you later work with characteristics, it's really good to have access to rotation and transformation in this very quick manner. Some menus in Blender are hidden at the side. When you look over here, there's this little plus symbol, and if we click that, we can open a big long sidebar with a bunch of information on it. I want to call your attention to these location values over here to see that when I drag this axis, when I drag the blue axis, you can see that the Z value is changing. It's growing larger as I put the ball higher in the air, and on the ground it's 0. One thing that you can also do, you can just go into these values. I have the ball selected, that's why I get to see the ball's values, and I can just click on here and enter a value, and it's going to position the object at this value. There are also a lot of things that you can do to feel more at home in Blender. If you are at any panel, you can go to the edge until you see the mouse cursor like this. You can right click and you can split an already existing window and give it a new part. And then you can actually fill those panels with different content depending on what you want through these drop downs here and here. And actually, even the 3D view that we have here, we could change to be something else. Now, what might be really good for us to have is a so-called dope sheet. I'm gonna put it here. And here we're going to put the graph editor, and you're going to see what they are for in a second, just to show you how you get access to them. Yeah, those workspace settings are specific to the Blender file. So if you made your file nice like this once, it will open with the windows that you left them with on any other computer. And in Blender, once again, we can go to frame 0 and we can actually put something on frame 0, but our animation is going to start playing at frame 1 because that is what is set as the start frame down here. So some people use frame 0 in Blender to store the default positions of a rig so that if you ever mess something up, you can just copy your frame 0 and you have restored everything to normality. We are just going to go to frame 1 for now and going to define our starting position, which is the ball up in the air. To get it in the air, we're just going to drag the blue axis so it is only moving along the blue axis. Going to put it a little bit in the air. And now we need to tell the software to keep this position in mind. This position right here needs to be tied to the frame. And to do that, we hit I on our keyboard and it's asking us what value it should set a keyframe for. Most of the times you want to click location and rotation. We only change the location, so we just want to save the location value for now. Click on that and you see stuff happening in the dope sheet and in the graph editor. What it did in the dope sheet is just showing us that on this frame 1 it has keyframe values stored, and we can actually look at what keyframe values it has stored. It has stored keyframe values for location X, Y, and Z. Now, one thing that will make your work a lot easier is if you activate this button down here, which is the auto key button. The thing is, if we don't have this on and we just would go to frame, let's say frame 18, and we're gonna position our ball somewhere else, once we move the cursor, the time again, it will jump back to the previous set keyframe. It didn't set a new keyframe for our new position. If we hit this auto key button, what it will do is it will actually record a keyframe at the current position if we move an object. If we move an object on frame 15, you can see we have new keyframes here on the dope sheet. What else can we see is that here this value is actually held. Like the X location keyframes, this keyframe and this keyframe, they have the exact same value, namely 0, as you can see here. X and Y are both 0 on both keyframes. That's why they have this bar in between. But the Z location has a different value on this keyframe than it has on that keyframe. And that's why there's no bar here to indicate that the computer is doing the interpolation between those two frames. And that is the big difference that we have between drawing frame by frame and using a keyframing software. In a keyframing software, you just set keyframes within a larger distance on the timeline, and the computer is calculating how the object moves in between there. And I say it once again, this is not a thing exclusively for 3D. There's many 2D software that works with rigs in a similar way. It might be called different, like Flash, Adobe Flash, now Adobe Animate calls it motion tweens, but it's the same method. You put an object there, tell the computer keep this coordinate in mind. X frames later, you put another keyframe, you tell the software keep this new coordinate in mind and interpolate between those. You can navigate in the dope sheet in a similar fashion how you navigate in the 3D view. If you use the mouse wheel, you can zoom in and out. If you click the middle mouse button, you can shift the view around. And what I would like to do right now is to move our test frame that we just put somewhere. I want to move that on frame 13, so we have the same timing as we had in our 2D version. To move and select keyframes, first of all, you can use the right mouse button, and if you click on a keyframe in the dope sheet summary, it's gonna select everything that is under it. We can also just select specific values. Like if we just want to move around or copy the X, Y, or Z location, we can just go in and just hit just select that keyframe. For any keyframes that we have selected, if we hit G, we can move them around. And this is also a key that I can use in the 3D view. If I'm in the 3D view and I hit G here, I can also move a 3D object around. But, you know, most of the time it's very helpful to actually use the axis so that I know exactly what axis I'm moving. In my case, I don't want to move a specific coordinate. I want to move the entire thing. So I click on the dope sheet summary and move that to frame 13. Just a couple frames back for me. There we have it. And I'm also not sure. I don't think we hit 0 exactly. I don't think we hit 0 exactly in the Z location, so we can go on this frame, make sure you are on the correct frame. If you are, you should see those values in yellow. That means that there is a keyframe set here, and we can just go in and put in 0 to put the ball exactly on the ground. Now we have the ball going from top to bottom in 12 frames, and again, this is our height of 1.20 meters. We can make the ball go back up by copying and pasting a previous keyframe. We just need to select the keyframe of our first position by using the dope sheet summary. We can hit Ctrl C and then go to frame 25 and hit Ctrl V. If you now play this, I hope you will notice that something isn't quite right here. Like, what is going on? This is looking more like a yo-yo. It's slowing down and then coming back up. And we can figure out what exactly is going wrong by using the graph editor. And to do that, we first need to select our object. And there you can see already some things appearing. And what we want to focus on, of course, is the Z location. We can make everything else invisible and just click on the Z location because that is the only thing that we animated so far. In the graph editor, you can hit the home button, or on my keyboard is the position 1 button, to zoom in on the current view, on everything that you can see in the current view, or you can just select everything and use the numpad comma key, the same key that you can also use in the 3D view to focus on an object. You can use that also in the graph editor. And now we can get a nice view look at how our motion looks on a mathematical graph. Doesn't that sound exciting? So it's time to dig into what an animation curve is. And don't worry, it's not too complicated. You will develop a feeling for it relatively quickly. It basically is a coordinate system that you might remember from math or physics class. At the x-axis, we have just time. We have frame 1, 2, 3, 4, 5, 6, 7, 8, just the passing time on the x-axis. On the y-axis, we have the transformation value. And in our case, this is the Z location. And if you look at our example here, we have a very high Z location. This is the highest Z location, and then it's coming down at first slowly, and then the distances grow larger and larger. Maybe let's have another look at the 2D animation that we already did. Let's make 2 animation grids here. At the x-axis, we have time, so we have frame 1, frame 2, frame 3, 4, 5, 6, 7, 8, 9, 10, 11. And here we have the same. And let's have a look what that actually means. Now, on this axis, of course, we don't have a falling ball. We have a ball going from left to right, but let's pretend it's falling and it has its highest value, let's say value 10, here, and then in the next frame it's going down by 1 value, and it's going down by 1 value again, and so on. So it's always going 1 frame further in time and 1 value down in the coordinate system. 1 frame further in time and 1 frame further in the 1 unit further in the coordinate system. Another frame down and another unit in the coordinate system, and so on. So for linear, we get a straight curve like this, because the distance going down and to the right is always the same. It's just a straight curve. Now, in the case of an ease, this distance here is smaller than a full unit. So instead of a full unit, it's for the beginning, it's still staying up here and only gradually catching up speed. And as you can see, those distances, they're like almost 2 units compared to the other ones. So here, for example, we have a difference of 2 units. And then in this case, we have an ease in again. So at this end, the units, the difference between our frames are getting smaller and smaller again. And in the graph, this is looking like this. So what we have now is an S-curve. Now, if you look at the curve in Blender, we can recognize this S shape, but we don't want to have a ball that is easing out and then easing in again. What we actually want is what we have in the 2D animation as well, just an ease out because the acceleration of gravity is kicking in, and then it's at its highest speed right before it hits the ground, and at the highest speed right when it starts jumping up again. So there is no ease here, there's no softening at the curve. And in Blender, we can go right into the curve and manipulate them. Specifically, what we need to change is this middle frame that's here in the dope sheet, and that is here in the curves. And we can select those curve points with the middle mouse, with the right mouse click, and we can select those tangent handles to change the appearance of our curve. Now, if we grab the left tangent handle, we can make the left side of the curve look a lot better. This is kind of what we want. We want to have an ease at this one side, and then we want it to go down with no ease in. But what have we done here? It's just shooting over the point, and causing some kind of it will go through the ground here, as you can see. And these things you kind of want to avoid because they get really difficult to control. You should preferably always have a point that you have the full control over at the top of such a curve. Now, what we need to do to shape the curve into the way that we need it, we need to select that keyframe that we want to change and go into the key menu of the graph editor and change the handle type to free. And now we can actually select each tangent handle individually and shape them how we want them to be. And this is the shape that we want to be going for. We want to only have the ease out here and this ease in here, and around the impact, it's just, it's at the highest speed. It doesn't know that it is about to hit the ground. It's just gonna hit the ground full speed, and then all the energy is directly transferred back into the ball, and it's jumping up again. Now we can set this up as a loop again if we go to the end frame value here and enter 24. And now we can play our animation by either hitting the play button here or using the keyboard shortcut Alt-A. And there we have it, a ball that is accelerating at the top and just going full speed into the ground at the bottom. And now I would actually like to invite you to play around a little bit with the 3 keyframes that you have. In 2D, this is a little bit more difficult because to play around with stronger easing or weaker easing, you would have to redraw all those frames. But in 3D, you only have the tangents of 3 keyframes that you can play around with to get vastly different feels of the ball bounce. Now, let me show you what I mean. You could just go in and, for example, experiment with the length. What did we say? 2 seconds for a 20-meter fall. So let's select all the keyframes with A. And if you put this green timeline cursor all the way over here, you can hit S for scaling the keyframes. And you can scale them to be at roughly at the 2-second mark, which would be 24 times 2 would be 48, so around here-ish. And then you can play this back, and it will look like a fall from a 20-meter distance. Then another thing that you can experiment with is you can grab the tangent handles and pull them out further and just see what happens. Oh, I just want to have the tangent handle and just see what happens. Now it's a real slow fall at the beginning, and then it gets very, we can even exaggerate that even more. If we can make it even faster at the end. Let's see how that looks. Yeah, it doesn't look correct, but you know, we can use this to find some interesting results that we might want to use in some more cartoony animation. Really, don't be afraid to just play around with these parameters and to try different speeds and different steepness for the tangents and different lengths for the tangents to get a little bit of a feel for what is doing what. Another nice thing that I would like to show you is, let's maybe revert this to our original timing, to the timing from 1 meter 20. There we have it, all back to what it was before. A bit strong here. Because overall, an object always has to keep its volume. Show you what I mean right here. If I have a ball and I squash it on the ground, if I would squash it like this, I would have all this mass that is gone, I don't know where. It just disappeared. The mass of the object needs to be the same in total. So what it does, it goes out to the side and looks like this, or maybe a little more like this. So this mass up here went into the sides. And to do this in Blender, what we can do is to squash it down by pressing S and the middle mouse button, pressing it down, and then making it bigger again so that it also goes out in size. This value is not really recorded in a way that is useful for us, so I'm going to revert it at first for now. What we need to do first is record the scale value, the normal scale that our ball has, and you can see it here. It's just 1, 1, 1. That is the default scale. Now we can put a keyframe in the way that you already know by hitting the I key and key scaling, but another thing that we can do is to actually key values in Blender on the value slider. We can hover over over all of these scale values and press I, and by doing so, we just set a keyframe. You can see it here. Here's XYZ scale. got a keyframe here, we got a keyframe from the auto key. It did set a keyframe, but you know, it's the same as we can see through the bar. Nothing happens between those values. And of course, we also need the same keyframe at the end again. So for whatever we are doing here when it hits the ground, it needs to normalize by the time that it comes back up. I do see a lot of people doing the bouncing ball the wrong way, and I don't understand why they don't see that this is not really working, is that they go to this middle position and then they squash the ball. First of all, they don't squash it the right way, and that they need to also make it go out again, but you know, they just squash it. And if we play this back, you should see that this looks rather odd. It's squashing while it is on the way down. And we can really not leave it that way, because the reason why it squashes is because it is hitting the ground. Because it is hitting the ground, the energy of the hit is causing the ball to distort. So it cannot start squashing while it is on the way down. What we can do is we can take the XYZ scale value from here. And if you want to copy and paste in all of these channels, you need to select them with Shift. And then we can select all of these three and just hit Control-C. And we're gonna paste them right before the ball hits the ground, because on that frame, the ball was still not squashed. It didn't hit the ground yet, so there's no reason to squash. And on the next frame, we actually have the squash happening. And then usually the ball doesn't need the whole way up to go out of its squashed form again, but is out of the squash relatively quickly. And because we just copy and pasted the default values, we can paste them here as well. And then we have a ball squashing only on impact. And this, of course, is a very, very short moment in time. We can barely see the ball being squashed there at the bottom. And one thing that I like to do with bouncing balls is to have them on the ground for multiple frames. I mean, we can do that with the dope sheet, but maybe it would be nice to see what we're doing in the graph editor. So let's select our object and let's focus on the location values. Maybe let's do it in the dope sheet. That's easier to see. So what I want is for these location values, again, we need to select them if we want to paste all three of them. I'm gonna copy them. I want them to be held for 1, 2. Let's maybe hold it for 3 frames. Let's see what happens. And I pasted them again. Now we also need to shift the last key, because otherwise our ball would need a shorter amount of time to come back up than what it needed to come down. So I need to shift it for the same amount, hitting G and going 1, 2 to the right. Now, as we can see in the curve editor, something is happening here, namely it's hitting the ground and is coming back up and then going back to the ground again. This is not what we want to happen. We want it to stay on the ground. And all we have to do is just click on the keyframes and put the tangents to where we want them to be. And now we have the ball hitting the ground, staying there very squashed, de-squashing, and then going back up. Maybe it could also not be fully back into its old shape at this position. So we look for the scale and shift this 1 frame further. Or yet another frame? Yeah, like this. And now if you play this, we have a few more frames to see the ball on the ground. Let's put it back into a loop. Now at frame 27. And yeah, see how we just defined the squash a lot more. Maybe we could make the fall a little softer. Let's see. See how this looks. Now this middle position, of course, gives us one more position to play with. You could even make it even longer, make it shorter. You could experiment how it looks when the ball is not squashed on this first impact frame and gets squashed while it is on the ground. You could try different speeds. You could squash it only a little bit, you could not squash it at all, and just see how these different things look. Overall, I have to say, if you followed along here, congratulations, you know now the very basics of ball bouncing in 2D and 3D. Now there will be more free tutorials like this one, but if you want more right now, please get our premium bonus tutorial. By purchasing it, you make sure that we can make more free content and we can make it quicker and better. And on top of that, you will get more exercises. You will get better at animation faster. In the premium bonus tutorial, we have a look at how you can animate a floppy tail on the side of your bouncing ball, both in 2D and with an actual rig. We're gonna have a look at the physical law of inertia, which is the law that explains why standing in a driving bus is so difficult, and how it translates to the animation principles of drag, follow through, and overlap. On top of that, you get access to the Animator Island Elite Facebook group, where you can post your work, you can get feedback on your demo reel or shot that you're animating on from me or other members from the group. There also will be exclusive critiquing events where I talk about the animations submitted in this group exclusively for the group members only. So if you want to be a part of that, we are selling this not for $24.99, but for $19.99. And all you have to do is to click the button around this video, and yeah, please, if you want to support us, get the premium bonus tutorial and become an even better animator. Thank you for watching.